imagine. For a moment, the earth seen from far above, a soft blue marble, wrapped in slow white clouds, turning quietly in the dark. Most of what you see is water. The great oceans cover almost 3/4 of the surface, and from this height they look smooth and calm, like a pane of dark glass. But the calm is only on top. Below that shining skin, the water grows colder. It grows darker. It grows heavier with every meter you sink. Now, let yourself drift down, past the sunlit shallows where fish flash silver, past the dim blue middle waters where light begins to fail, past the level where almost no sunlight reaches at all, where the water turns to a kind of soft, endless night. Keep going, down past 1,000 meters, down past 2,000, down to where the pressure would crush a submarine made of ordinary steel, and where the temperature hovers just a few degrees above freezing. Here, on the floor of the deep ocean, the world is mostly flat and quiet. Soft grey mud stretches in every direction. A slow snow of tiny dead things drifts down from far above, settling like dust in an old room. For a long time, scientists believed this place was nearly empty. Without sunlight, they reasoned, there could be no plants. Without plants, no food. Without food, no life worth mentioning. The deep sea floor, they thought, was a vast and lonely desert. Then, in certain places along the great cracks in the Earth's crust, the floor changes, the mud parts. Strange stone towers rise into the dark, some no taller than a chair, some taller than a 4-story building. From their tops, hot fluid pours out in shimmering clouds. Some clouds are black as soot, some are pale and milky white. Around these towers, the cold, dark water teems with living things that should not, by any old rule book, be there at all. Before we go further, the planet has a new quiet wonder to share every night. If you'd like one waiting for you each evening, subscribe and let it come to you. These towers are what we call deep sea chimneys. They are also called hydrothermal vents, which simply means hot water openings. They form where seawater seeps down through cracks in the ocean floor, touches the hot rock below, and rises again, carrying minerals and gases. As that warm fluid meets the cold ocean, the minerals fall out of the water and harden layer by layer into stone. Slowly, over years and centuries, the chimneys grow upward into the dark. What makes these places so quietly astonishing is not only their shape, or their heat, or the strange creatures that gather round them. It is a question they have raised, a question that scientists have been turning over carefully for the past few decades, like a smooth stone in the palm of the hand. The question is this: could life on Earth have begun in a place like this? Not in a warm pond under a soft sun, as people once imagined, but here, in the cold dark, around one of these stone towers at the bottom of the sea. It is, for now, an open question. Some researchers believe the deep vents are the most likely cradle of all living things. They point to the chemistry, to the minerals, to the steady flow of energy in a place that never sees the sky. Others believe life more likely began in shallow pools at the surface, warmed by sunlight, dried and wetted again and again by ancient tides. Both ideas have evidence behind them. Neither has been proven. The puzzle remains unsolved. Over the next few hours, we will sit gently with that puzzle. We will visit chimneys black as ink and others pale as bone. We will pass tube worms with hidden partners inside them and tiny microbes that may be our oldest distant cousins. We will think about hydrogen and carbon and the first faint stirrings of something we now call life. We will not try to settle the question. The question may not be settleable yet, We will only wonder about it together, slowly, while the ocean turns above us and the dark water holds its secrets close. So let your shoulders soften, let your breathing slow. Picture that blue planet again, turning quietly in the dark, with its vast hidden floor and its small bright towers far below. The chimneys are still there tonight. They are still pouring out their warm, cloudy water into the cold. And somewhere among them, the answer to one of our oldest questions may be waiting, patient as stone, for someone to finally understand it. Let us begin with something simple. A hydrothermal vent is a crack in the floor of the ocean where hot water rises up out of the rock. That is the whole idea. In its plainest form, cold seawater seeps down into the cracked crust of the seafloor. It meets the hot rock below. It heats up, picks up minerals, and rises back out into the dark sea, sometimes through tall stone chimneys built grain by the water itself. That is far hotter than any kitchen oven on its highest setting. It does not boil though, because the weight of the sea above pushes down with such force that the water stays liquid. 2 miles of seawater pressing on every drop will do that. The water can be hotter than steam and still flow like a clear dark soup. The chimneys themselves are made of minerals that fall out of the water as it cools. Iron, copper, zinc, calcium, sulfur, all dissolved in the rising fluid, all settling into solid stone the moment they meet the chilly sea. Bit by bit, layer by layer, the chimney grows. Some are short and squat, like stone stumps. Others rise like crooked church steeples, 60 feet tall, 90 feet tall, sometimes taller than that. One famous chimney, nicknamed Godzilla, stood about 15 stories high before it eventually toppled. Imagine a small apartment building, leaning slightly, blooming on the floor of the Pacific. These vents sit deep. Most are found between 5,000 and 12,000 feet below the surface. In feet, that does not sound like much. In meaning, it is another world. No sunlight reaches that far, none. The last weak blue light of the surface gives out around 3,000 feet. Below that, the ocean is pitch black, the kind of black your eyes cannot adjust to, because there is nothing for them to see. The water is just above freezing. The pressure would crush a soft body in an instant. And there, in that cold and dark and crushing place, the vents pour out their hot, mineral-rich fluid like little burning rivers leaking from the earth. The chimneys are not rare. They sit along the mid-ocean ridges, the long mountain chains that run down the middle of every major ocean basin. If you could drain the seas, you would see a seam of mountains stretching for 40,000 miles, wrapping around the planet like the stitching on a baseball. Wherever the seafloor pulls apart along that seam, hot rock rises close to the surface, and where hot rock meets seawater, vents tend to form. So vents are scattered in many thousands of fields across most of the world. We have only mapped a small share of them. Most have never been seen by human eyes or by any camera. Until the late 1970s, no one had seen one at all. Biology textbooks taught that all life on Earth ultimately drew its energy from the sun. Plants caught the light. Animals ate the plants. Other animals ate those animals. The deep sea was assumed to be a thin, slow place, scraping by on whatever crumbs drifted down from above. Then, in 1977, a small submersible called Alvin descended onto the Galapagos Rift in the eastern Pacific. The scientists inside were looking for hot water. What they found stopped the field of biology for a moment and made it start over. They found towers leaking warm fluid, and around the towers a crowd of living things, pale crabs, clams the size of dinner plates, forests of long red-tipped worms, standing in soft white tubes, mats of bacteria coating the rocks like spilled paint. A whole ecosystem, dense and busy, with no sunlight reaching it and no clear food falling from above. The animals were feeding, somehow, on the chemistry of the vent itself. They had been doing so, probably, for a very long time, while the textbooks said it could not be done. That single dive opened the question we will sit with through this whole long night. If life can thrive in a place we thought was empty, drawing its energy from rock and water rather than from sunlight, then maybe sunlight was never necessary at all. Maybe life began somewhere very much like this. Or maybe it began somewhere else entirely, and the vents are simply a strange, late chapter. We do not yet know. We may not know for a long while. For now, picture the small white lights of Alvin drifting across that warm, crowded floor, and the dark sea closing in around them. To understand how a black smoker is born, you have to travel back in your mind to a place where the ocean floor splits open. Picture a long, slow seam running across the dark seabed, thousands of feet beneath the waves. This seam is where two great plates of the Earth's crust slowly pull apart from each other. They move only a few inches each year, about as fast as your fingernails grow. As they part, the molten rock beneath rises up to fill the gap. That molten rock is called magma. It sits just below the thin new crust, glowing hot, sometimes only a mile or two beneath the seafloor. The water above is icy cold, just a few degrees above freezing, and yet, through tiny cracks in the rock, that cold seawater begins to seep down. Here, it travels through the stone like rain through soil, sinking deeper and deeper into the crust. As the water sinks, it gets hotter. It passes through layers of fresh basalt, the dark, heavy rock that makes up the floor of the deep sea. The pressure down there is enormous, more than 200 times the pressure at the surface. Under such pressure, water can grow hotter than seems possible without ever turning to steam. By the time it nears the magma chamber, it can reach temperatures of 700 degrees Fahrenheit or more. It is still liquid, but only barely, and it is no longer the same gentle seawater that began the trip. Down in that hot, squeezed darkness, the water becomes a kind of chemical thief. It pulls metals and minerals out of the surrounding rock. It strips away iron, copper, zinc, and sulfur. It loses its oxygen and gains a faint, acidic bite. Now it is a strange, mineral-rich brew, dense with dissolved metals, and it begins to rise. Heat lifts it. Pressure pushes it. It moves back up through cracks toward the seafloor, faster than it came down. When this hot, dark fluid finally bursts out into the cold ocean, something remarkable happens in an instant. The chilled seawater shocks the rising plume. The metals it carried can no longer stay dissolved. They snap into tiny solid particles, mostly dark sulfides, and form a billowing black cloud that pours upward like smoke from a chimney. This is where the name comes from. The fluid itself is clear when it leaves the rock. The blackness is born only when hot meets cold. Some of those mineral particles drift away in the deep currents. Others fall straight back down and settle around the opening. Layer by layer, they build a rim. The rim grows into a ring. The ring grows into a tube. The tube grows upward, sometimes a few inches a day, until a tall, dark spire stands on the seafloor. Some of these spires reach the height of a 4-story building. A few have grown taller than that before toppling under their own weight. The shapes they make are strange and beautiful. Some look like crooked towers leaning together. Some look like organ pipes. Some grow shoulders and arms where side vents open. The walls are porous, full of tiny channels where hot fluid still seeps through inside. The temperature is searing. Just inches away in the surrounding water, it is near freezing. The chimney itself is a thin skin between two utterly different worlds. These towers do not last forever. Plumbing beneath them shifts. The cracks that feed them clog with their own minerals. A spire may stand for decades or centuries and then go cold and crumble. New ones rise nearby. The whole field breathes slowly, in a rhythm measured in human lifetimes, building and falling and building again along the seam and the crust. How long has this been happening on Earth? That is one of the open questions. Black smokers exist today, wherever plates pull apart, and the same forces have been at work for billions of years. Some researchers believe vents like these have been forming since the oceans first filled, more than 4 billion years ago. Others think the early Earth had different chemistry, and the vents of that distant time may have looked quite unlike the ones we see now. The rocks that might tell us have mostly been recycled back into the mantle, lost to the slow churn of the planet. So, when we picture a black smoker rising in the dark, we are looking at something both ancient and new. The process is old, the tower is young, and somewhere in that long, patient cycle of cold water sinking, hot water rising, and minerals settling into stone, there may be a clue about how our world came to be the kind of place where life could begin at all. Not every chimney on the seafloor breathes black smoke. Some of them whisper instead, releasing pale, milky fluids that drift upward like fog through cold, dark water. These are the white smokers, the quieter cousins of the black ones, and their chemistry tells a softer, stranger story. To understand why some scientists believe life may have begun at vents like these, it helps to walk slowly through what they are actually made of. A white smoker is not as hot as its black sibling. Where black smokers can blast water at 350 degrees Celsius or more, white smokers often release fluids at a cooler, sometimes only 40 to 90 degrees. The color comes from the minerals dissolved inside. Instead of iron sulfides which stain the water dark, white smokers carry lighter compounds. Calcium, silicon, and barium drift out in pale clouds. These settle into spires made mostly of calcium carbonate, the same mineral that builds seashells, chalk cliffs, and the bones of coral reefs. The chimneys look bone white in submarine headlights, ghostly and soft. The fluids that pour from white smokers are often alkaline, which is the opposite of acidic. The seawater around them is gently acidic, full of dissolved carbon dioxide. When these two fluids meet, they react. Tiny crystals form, walls grow, pores open inside the rock, no wider than a single cell. Some researchers believe these little pores may matter very much, though we will come back to that question in a later chapter. Think for a moment about where all of this material came from. The calcium in a white smoker chimney was once locked inside ancient rock. That rock came from molten magma. That magma rose from the mantle, the thick layer of slow hot stone beneath the crust, and the mantle itself formed more than 4 billion years ago, when the young Earth was still gathering itself from a swirling disk of dust and debris. That dust did not come from nowhere. Every atom of calcium in those pale spires was forged inside a star. Long before our sun existed, older stars lived and died across the galaxy. In their hot cores, simple atoms like hydrogen fused into heavier ones. Calcium, iron, silicon, magnesium, all of them were cooked inside stars that no longer exist. When those stars died, they scattered their elements into space. Some of that scattered material eventually clumped together to form our planet. The water itself may have arrived later, riding on icy comets and wet asteroids that struck the young Earth. We are not entirely sure of the proportions. Some water was likely here from the beginning, bound inside the rocks that built the planet. Some may have come from above, delivered across millions of years by frozen visitors from the outer solar system. The question of how much arrived from where is still open. What we do know is that the ocean, which now flows through white smokers, carries a memory of that long delivery. When seawater seeps down through cracks in the crust, it meets rock called peridotite. Peridotite is rich in olivine, a green mineral made of iron, magnesium, and silicon. Water reacts with olivine in a slow chemical change called serpentinization. The rock takes on water and transforms into a softer greenish mineral called serpentine. This reaction does several things at once. It releases heat, gently warming the surrounding stone. It releases hydrogen gas, which bubbles up through the system, and it makes the leftover fluid alkaline. Hydrogen is a quiet, simple thing, just one proton and one electron. Yet hydrogen is also the fuel of much early Earth chemistry. When hydrogen meets carbon dioxide in the right conditions, it can form simple organic compounds, the small carbon-based molecules that all life is built from. Whether this actually happened at the dawn of life, and whether it happened at vents like these, remains an open question. Some chemists have produced these reactions in the lab. Others argue that the conditions in real vents are not quite right, or that the molecules form too slowly, or that they wash away before they can do anything interesting. So a white smoker is, in a sense, a meeting place of deep time. Star-forged calcium, comet-delivered water, mantle-warmed rock, and atmospheric carbon all come together in pale, slow-growing towers at the bottom of the sea. The chimneys are quiet, the fluids are gentle, the chemistry is steady, not violent. Whether this gentleness was enough to nurture the first stirrings of life, or whether life began somewhere else entirely, is a question we will keep returning to as the night goes on. For now, picture those soft white spires rising in the dark, glowing far. Far out in the middle of the Atlantic Ocean, about half a mile below the waves, there sits a quiet field of pale stone towers. The first explorers who saw it gave it a fitting name. They called it the Lost City. The towers rise like the ruins of some ancient cathedral, soft and ghostly in the beams of the submersible lights. Some of them stand 60 meters tall. That is about as high as a 20-story building, but built from minerals instead of steel. The Lost City does not look like the black smokers we spoke of before. There is no dark soot pouring from its tops. There are no burning hot jets shooting into the water. Instead, the towers leak a milky warm fluid that drifts upward in slow, ghostly plumes. The water coming out is not boiling. It is closer to the warmth of a fresh cup of tea that has been left on the counter for a while. And yet, what is happening inside these towers may be one of the most important chemical stories on the planet. To understand the Lost City, we have to think about the forces pressing on it. The weight of all that seawater above creates enormous pressure. At that depth, every square inch of stone holds up tons of water. Pressure changes the rules of chemistry. Gases dissolve differently, minerals form differently. Reactions that would never happen on the surface can quietly unfold in the dark. There is also the pull of the earth itself. Beneath the Lost City lies a kind of rock called peridotite. Peridotite usually rests deep inside the mantle, the hot layer below the crust. But in this part of the ocean, the slow shifting of tectonic plates has pushed that deep rock upward. It now sits close to the seafloor, where seawater can reach it. When seawater seeps into peridotite, A slow reaction begins. The rock takes in water and changes into a new mineral called serpentine. This process is called serpentinization, and it is one of the gentlest yet most powerful forces shaping this strange city. Serpentinization gives off heat, not the violent heat of a volcano, but a steady, slow warmth that can last for tens of thousands of years. It also gives off hydrogen gas, a simple fuel that some microbes can eat, and it makes the surrounding water very alkaline, which means the opposite of acidic. Picture the soapy feel of dishwater. That is what the fluid leaking from the lost city feels like. Warm, slippery, full of hydrogen, and rich in dissolved minerals. These conditions slowly build the towers as the alkaline fluid meets the cold, slightly acidic seawater. Minerals fall out of the water like snow. They settle onto the chimney walls, layer by layer. Over centuries, the towers grow taller. Some of the chimneys of the lost city are believed to be at least 30,000 years old. A few may be much older. They are not blasted out in a sudden burst, like a black smoker. They are sculpted, slowly, by a quiet partnership between hot rock, cold water, and time. The forces involved are gentle compared to a deep-sea volcano, but they are persistent. Pressure squeezes, gravity pulls deep rock up to meet the sea. Heat from the chemical reaction rises and drives slow currents inside the porous chimneys, and the chemistry sets up tiny gradients, places where alkaline fluid meets ordinary seawater, where electrons want to move from one side to the other. Some researchers find these gradients deeply interesting. They wonder whether something like them, long ago, may have sparked the very first stirrings of life. That is one of the open questions we will sit with in the sections to come. The lost city was only discovered in the year 2000. Before then, scientists did not know that vents like this could exist. They had spent a generation studying the hotter, blacker chimneys, and they assumed those were the model. The lost city showed that the seafloor could shelter slow, warm, alkaline systems too, powered by nothing more than the meeting of rock and water. How many more such fields are hidden across the ocean floor? No one yet knows. Most of the deep sea has never been mapped in close detail, so picture it now in the soft dark. Tall, pale spires, weeping gentle warmth into the cold. Tiny shrimp and microbes clinging to their walls. The pressure of an ocean overhead, and below, the deep rock slowly drinking the sea, breathing out hydrogen, building towers from nothing, on a quiet timescale, far longer than any human life. Why this place exists where it does, and what it may once have given rise to, remains an open and tender question. To understand where the first life may have flickered into being, it helps to picture the place where seawater meets the melted crust. The numbers are strange. They are worth sitting with for a moment, the way you might sit with a slow tide. Start with the ocean above the vents. The average depth where black smokers form is around 2,000 meters. That is 2 kilometers of water pressing down. If you stacked 6 Eiffel Towers on top of one another, the top of the highest tower would just barely break the surface. At that depth, the pressure on every square inch of chimney is roughly 200 times what you feel on a quiet beach. A firm coffee cup carried down to that depth comes back the size of a thimble, its walls crushed thick and tight. Now picture the temperature gradient across just a few centimeters of rock. On one side of a chimney wall, the seawater hovers near 2 degrees Celsius, barely above freezing. On the other side, the rising vent fluid can reach 350 degrees, hotter than a kitchen oven set to broil. The only reason that fluid does not boil is the crushing pressure holding it together. So, across the thickness of a chimney wall, sometimes no thicker than a pancake. You have a temperature difference of nearly 350 degrees. That is one of the steepest natural temperature gradients found anywhere on the planet. The chimneys themselves grow at a pace that feels almost alive. Some black smoker spires can rise as fast as 30 centimeters in a single day during a strong eruption, faster than a tomato vine in summer. Others creep upward over centuries, gaining a millimeter here, a millimeter there. The tallest known chimney, before it toppled, reached around 60 meters from the seafloor. That is roughly the height of a 20-story apartment building, standing alone in the dark, with no foundation but cooled mineral. Underneath all of this is the crust itself. The oceanic crust is surprisingly thin. On average, it is only about 7 kilometers thick, which sounds like a lot until you compare it to the Earth as a whole. If the planet were shrunk to the size of an apple, the oceanic crust would be thinner than the apple's skin. Thinner, and the heat below that skin is what powers the entire vent system. Where seawater seeps down through cracks in this thin crust, it travels a long, slow path. The water can sink as deep as 2 or 3 kilometers below the sea floor before it meets rock hot enough to drive it back up. The full round trip from the cold ocean down into the hot rock and back out through a chimney can take years. Some estimates suggest decades. The molecules of water that puff out of a smoker today may have started their descent before you were born. The heat source is the planet's own slow cooling. Earth's interior holds an enormous reservoir of thermal energy, much of it left over from the formation of the planet 4.5 billion years ago, and much of it generated by the slow decay of radioactive elements in the mantle. That heat leaks outward at a rate of about 90 milliwatts per square meter on the seafloor. That is a tiny trickle, weaker than the heat from a single Christmas light spread over a card table. But spread across the global ocean floor, it adds up to a steady, planet-scale furnace. Now, think about how much of the ocean's water passes through these systems. One estimate suggests that the entire volume of the world's oceans cycles through the hot crust roughly every 10 to 20 million years. Every drop of seawater eventually takes a turn deep inside a vent. Over the 4 billion years that oceans have existed, that water has been chemically reworked again and again, like dough kneaded by the slow hands of the earth. The chimneys are small compared to the ocean, and the ocean is small compared to the planet. A single field of vents might cover an area no larger than a city park, but these tiny patches scattered along the mid-ocean ridges may have been where the most important chemistry in Earth's history quietly took place. Whether that is true remains an open question. Some researchers argue the energy and the scale at vents are exactly what early life needed. Others wonder if the heat was too fierce, the dilution too vast, the chemistry too quickly washed away. The numbers do not settle the question. They only make it more wondrous to sit with, here in the dark, while you drift towards sleep. Imagine drifting down through the dark water, slowly, with no need to breathe, no need to hurry. The surface light fades within the first few hundred meters, and below that, the sea becomes a deep, even black. Then, after what feels like a long, quiet fall, a faint glow begins to take shape below you. Not sunlight, not anything like sunlight, a dim, almost dreamlike shimmer, the color of warm copper and old gold, rising from the seafloor. You settle gently above a strange country. The ground here is uneven and broken, scattered with rocks the color of wet ash. In places, the rock looks fresh and glassy, like dark candle wax that has cooled in odd shapes. In other places, it is dusted with a fine pale sediment, soft as flour. And rising from this floor, like the ruins of some forgotten city, stand the chimneys. Some are short and stubby, only as tall as a person. Others rise the height of a small building, leaning, twisted, layered with knobs and shelves, and curling lips of mineral. The black smoker chimneys are dark as charcoal, streaked with rusty reds and deep blues where iron and copper have settled into the stone. Their tops pour out plumes of inky fluid that bloom upward into the cold water like slow ink in a glass. The plumes look almost solid at first, then break apart into clouds of tiny black grains that drift sideways on the deep current. The white smokers are gentler to look at. Their walls are the color of pale bone, sometimes a soft cream, sometimes a chalky gray with hints of green. The fluid that rises from them is milky and slow, more like steam than smoke. It curls upward in lazy ribbons, catching the dim glow and turning it almost silver. If you reach out, you would feel the temperature change in bands. A few meters from a chimney, the water is near freezing. Closer in, you pass through layers of warmth, like ribbons of bath water laid through ice. Right at the chimney's mouth, the fluid can be hotter than anything that should be liquid at all, kept from boiling only by the immense pressure of the sea above. The chimneys do not stand alone. They cluster and lean against each other and grow into one another over the years. New spires sprout from the sides of old ones. Older spires crumble and fall, and their broken pieces become the ground for the next generation. The whole field looks, in some places, like a slow stone forest. In other places, it looks like a cathedral that built itself without a plan. The colors here are not the colors of the surface world. There is no green of leaves, no blue of sky. Instead, there are quiet, mineral colors. The bronze of weathered copper, the dull yellow of sulfur crusts, the bruised purple of certain iron stains, and there is the strange soft white of bacterial mats that cover the warmer stones like patches of damp snow. These mats are alive. They are thick colonies of microbes, billions of them, feeding on the chemistry pouring from the rock. Around the bases of the chimneys, the seafloor often slopes into shallow pools and channels where heavier fluids settle. Some of these pools shimmer faintly, holding water that is denser, saltier, hotter than the surrounding sea. They look almost like pools of mercury, with a thin, trembling surface. Tiny shrimp drift above them. Tail crabs walk slowly along their edges. A few delicate, ghostly fish hover in the dark like soft white flags. This is the surface of the cradle, if cradle is the right word. And here is where the central question quietly returns. Some researchers look at this scene and see in the layered minerals and the warm chemistry and the steady flow of energy the kind of place where life could have begun. Others look at the same scene and feel less sure. The chemistry is rich, yes, but the conditions are also harsh, and many delicate molecules would struggle to survive long in such fluids. One theory holds that the gentler white smoker fields, with their cooler temperatures and stranger chemistry, fit the picture better than the violent black ones. Another holds that no vent is right, and that the answer must lie somewhere else entirely, perhaps in quiet ponds on early land. For now, the chimneys simply stand. They release their slow plumes into the dark, and they build themselves grain by grain, and they hold their secret close. The cradle, if it is a cradle, is not telling. It only glows and bubbles and waits, while the deep water moves gently around it, as it has for a very long time. To understand a chimney at the bottom of the sea, you have to imagine something almost paradoxical. A tower, sometimes taller than a 10-story building, Rising from the dark ocean floor, no one carried the stones up. No one mixed the mortar. The chimney built itself, one mineral grain at a time, from the meeting of two waters that should not, by any ordinary logic, ever meet. The recipe begins deep below the seabed. Cold seawater seeps down through tiny cracks in the young ocean crust. It travels slowly, sometimes for years, sinking toward the hot rock that lies beneath. As it falls, it warms. As it warms, it begins to dissolve the minerals around it. Iron leaves the rock and enters the water. So do copper, zinc, and traces of gold and silver. By the time this water turns and rises again, it is no longer water as we know it. It is a hot, acidic, mineral-laden fluid, sometimes hotter than 400 degrees Celsius, kept liquid only by the crushing pressure of the sea above. Then comes the meeting. The hot fluid surges up out of a crack in the ocean floor and slams into near-freezing seawater. The temperature change is sudden and severe. In an instant, the minerals that had been dissolved in the hot fluid lose their place. They cannot stay in solution at such cold temperatures. They fall out of the water as tiny solid grains, like sugar crystallizing on the side of a cooling pot. Iron and sulfur join to form a dark mineral called pyrrhotite. Copper and iron and sulfur form chalcopyrite. Zinc and sulfur forms sphalerite. These grains settle wherever they can, and the place they settle most thickly is right at the rim of the opening, where hot meets cold most violently. That rim becomes a ring. The ring grows upward. The hot fluid keeps rising through its center. The cold water keeps lapping at its outside, and the wall between them keeps thickening. A chimney is born. Some of these spires grow at rates that almost defy belief, adding tens of centimeters in a single day during their fastest seasons. Others creep up more slowly. Many topple under their own weight, breaking and collapsing back into the dark, only for new ones to begin again on the rubble. If you could slice a black smoker chimney open and look inside, you would see something stranger still. The walls are not solid. They are layered, almost like the rings of a tree, with the youngest minerals on the inside and the oldest on the outside. Near the hot core, you find copper-rich minerals that need very high temperatures to form. Move outward through the wall and the temperature drops, and the minerals change with it, shifting to zinc-rich layers, then to iron sulfides, then to softer crusts of anhydrite, the calcium mineral that comes straight out of the seawater itself. The chimney is a kind of frozen map of temperature recorded in stone. The white smokers and the lost city towers build themselves a little differently. There, fluids are cooler and less acidic, and the minerals they leave behind are pale carbonates and softer sulfates rather than dark sulfides. There, chimneys can grow even taller, some reaching 60 meters into the dark water. They look more like cathedral spires than industrial smokestacks. Inside, their walls are riddled with tiny chambers, networks of pores no wider than a strand of hair, each one a little pocket where fluid moves slowly and chemistry has time to work. Those pores are part of why some researchers cannot stop thinking about these towers. A chimney is not just a pile of minerals. It is a structure with built-in compartments, built-in temperature gradients, built-in chemical differences between the inside and the outside of every wall. One idea is that these natural compartments could have served as the first containers for early chemistry, holding molecules close together long enough for something interesting to happen. A competing view holds that mineral compartments are too leaky, too unstable, too short-lived for that role, and that the real cradle of life must have been somewhere quieter and more enduring. Both ideas are still on the table. What no one disputes is the simple, quiet wonder of the thing itself. A vent opens in the seafloor. Two waters meet. Minerals fall out of solution in a precise sequence dictated by temperature and chemistry, and a tower rises into the lightless water, built by no hands, designed by no mind, following only the patient arithmetic of dissolved metals, finding their way back to solid form. Whether such towers also built the first life remains, for now, an open question. On the surface of our world, almost every living thing depends on the sun. Plants drink in sunlight and turn it into food. Animals eat the plants, and other animals eat those animals. The whole chain leans in the end on that golden light pouring down through the sky. For a very long time, this seemed like a simple rule of life. No light, no food. No food, no creatures. The deep sea broke that rule. Down at the vents, far below the reach of any sunbeam, whole gardens of living things crowd around the warm chimneys. Crabs the color of pale milk creep along the rocks. Shrimp, with strange light-sensing patches on their backs, swarm in glittering clouds. Tube worms taller than a person sway in the dark current, their soft red plumes pulsing like slow, patient hearts. None of these creatures has ever seen the sun. None of them needs to. The trick they have learned is called chemosynthesis. Where plants on land use sunlight to build sugar, certain microbes at the vents use chemicals instead. They take hydrogen sulfide, that rotten egg gas seeping out of the chimneys, and they pull energy from it. They take in carbon dioxide from the seawater and stitch it into the same kinds of sugars a leaf might make. The sun has nothing to do with it. The earth itself is the power source. These microbes are the base of the whole vent community. They drift in the water, coat the rocks in soft mats, and live tucked deep inside the bodies of larger animals. Every tube worm, every clam, every white crab is feeding, in one way or another, on this strange chemical harvest. A whole food web blooms in total darkness, fed by heat and minerals from beneath the crust. Life at the vents pulses to its own rhythm. A chimney may grow steadily for years, sending out a thick plume of dark, mineral-rich water. Around it, the animals settle in dense crowds. Then, without warning, the flow may shift. A new crack opens nearby. The old chimney cools. The water that once nourished the worms turns cold and quiet. The community fades. Empty white tubes stand in the gloom, like a small ruined city, and the crabs wander away to look for warmer ground. A few miles off, a new vent may already be opening. Fresh hot water meets cold seawater. Minerals begin to fall out of the fluid and stack into the start of a young spire. And somehow, larvae find it, tiny drifting young of tube worms and clams, and snails settle on the new rock and begin to grow. How they cross the dark miles between vents is still not fully understood. One idea is that they ride deep ocean currents in long, patient drifts. Another is that they're quiet stepping stones, small seeps and warm patches we have not mapped yet, that help them along. The question stays open. This rising and fading of vent cities has been going on for a very long time. The mid-ocean ridges have been venting heat and chemicals for billions of years. As the plates pull apart, new cracks form. As the chimneys cool, old ones collapse and turn back into rubble on the seafloor. The whole system breathes in slow geological time, building and unbuilding itself over and over. It is here that the central mystery begins to sharpen. If life can thrive in the dark on chemicals alone, then perhaps the first living things never needed the sun at all. Perhaps the cradle of life was not a sunlit pool on some ancient shore, but a quiet warm crack on the deep sea floor, pulsing with hydrogen and minerals. Some researchers find this idea very persuasive. Others wonder if the surface pools, with their cycles of wet and dry, sun and shade, offered something the vents could not. Both groups are still arguing, gently, in their papers and conferences. What is clear is that the rule we thought we knew, that life needs the sun, was never quite true. The earth has more than one way to feed its creatures, and the rhythms of the deep, the long, slow breath of the chimneys, the drifting larvae, the rising and falling cities of worms and crabs, suggest a kind of life that runs on the heat of the planet itself. Whether that older, deeper rhythm is also where it all began is one of the questions still waiting in the dark water. For now, the vents keep pulsing, the microbes keep working, and the strange pale animals keep gathering around the warmth, asking nothing of the sky above. Near the base of a black smoker, in water that should be far too hot and far too poisoned for anything to live, there is a forest. The trees of this forest are not trees at all. They are tube worms, some of them taller than a person, standing in dense pale clusters with bright red plumes waving at their tips. Their long white tubes rise from the rock like soft chimneys of their own, and the strangest thing about them, the thing that took biologists years to understand, is that they have no mouths. They have no stomachs either. They do not eat in any way that a creature on the surface would recognize. When researchers first pulled one up and cut it open, they found a body filled with a spongy red tissue, packed tight, looking almost like raw meat. Inside that tissue lived something else entirely, bacteria, billions of them. The worm and the bacteria were not two animals sharing a space. They were one living thing made of two. The arrangement is called a symbiosis, which simply means two kinds of life that need each other to survive. The tube worm provides shelter and a steady supply of the chemicals its partners crave. Its red plume, soft and feathery, pulls hydrogen sulfide and oxygen and carbon dioxide from the vent water, hemoglobin in the worm's blood. The same kind of molecule that makes our own blood red carries those chemicals down into the tissue where the bacteria wait. The bacteria use the chemicals to make food. Some of that food feeds the worm. Without the bacteria, the worm would starve in minutes. Without the worm, the bacteria would have no safe place to gather such a rich stream of fuel. Neither one is complete on its own, and this, in a quiet way, is part of what makes the vents so interesting to anyone wondering how life began. Cooperation at the chemical level is not unusual in this strange ecosystem. It seems to be the rule. The neighbors of the tube worms are just as odd. Pale crabs pick their way across the rocks, blind or nearly so, feeling for scraps with long legs. Ghostly shrimp swarm in shifting clouds, some with patches on their backs that may sense the faint glow of the hottest vent water. Clams, the size of dinner plates, settle into cracks where warm fluid seeps up between cooler currents, and inside their shells, too, live partner bacteria doing the same chemical work. Snails, with shells reinforced by iron, cling to the chimney walls. Limpets graze on bacterial mats that coat every surface in soft white and yellow drifts. Around it all, the cold, dark water of the deep sea presses in. Step a few meters away from the vent, and the forest ends. The rock turns bare. The animals vanish. Each vent is an island of warmth and chemistry in an otherwise empty plain, and the islands are scattered across the seafloor with long, lifeless stretches between them. How the larvae of tube worms and clams travel from one island to the next, across miles of black water, is itself a question researchers are still trying to answer. Some larvae seem to ride deep currents for weeks. Others may sense chemical traces of distant vents the way a moth senses a flower. When a vent goes quiet, as vents eventually do, the entire forest dies. The hot fluid stops flowing. The bacteria inside the tube worms lose their fuel. The worms shrivel. The crabs wander off or starve. Within a few years, the chimney is just a cold stack of minerals, and the rock around it returns to silence. Somewhere else, perhaps not far away, a new vent has opened, and a new forest has begun to grow. This rhythm of bloom and silence has been going on, in one form or another, for a very long time. How long is one of the open questions. Some researchers think vent ecosystems like these may stretch back billions of years, perhaps almost to the beginning of life itself. Others suspect that the tube worm partnership is much younger, a more recent invention, layered on top of a far older microbial world. The fossils are unclear. The chimneys themselves rarely survive intact in ancient rock, and soft creatures like worms almost never leave a trace. What we can see today in the living forests around the vents is that life here has solved the problem of darkness by working together. One body, two species, one shared chemistry. Whether that pattern of partnership is something new or something nearly as old as life itself is a question still drifting in the warm water around the chimneys, unanswered, waiting. Down in the warm water that pours from the vents, there lives a group of creatures so strange that scientists had to invent a new branch of the tree of life to hold them. They are called archaea. They look, under a microscope, much like ordinary bacteria, but their chemistry is different. Their cell walls are built from different molecules. Their genes read in different ways, and many of them love conditions that would kill almost anything else. Some archaea thrive in water that is hotter than a kitchen oven. One species, found near deep-sea vents, can grow in water that reaches 122 degrees Celsius. That is well above the boiling point at the surface. Down at the vents, the crushing pressure keeps the water liquid even at those temperatures. The microbe simply goes on living, splitting in two, eating hydrogen and sulfur, untroubled by heat that would cook a steak in seconds. Other archaea prefer acid. They live in pools so sour they could dissolve metal. Some live in water as salty as a brine pond. Some live deep inside solid rock, miles below the seafloor, eating gases that seep through tiny cracks. Wherever the conditions seem impossible, you can often find an archaeon quietly making a living. Scientists who study the tree of life have noticed something curious about these heat-loving microbes when you compare their genes to the genes of every other living thing on Earth. The hottest archaea sit very close to the base of the tree. They branch off near the root. Their chemistry looks ancient. Their way of harvesting energy from hydrogen and carbon dioxide is simple, almost primitive, the kind of metabolism you might expect from the earliest cells. This has led some researchers to wonder whether the heat-loving microbes of the deep vents are the closest living relatives of the very first life on Earth. Not our ancestors, exactly, but distant cousins who never left the cradle, while the rest of life moved into sunlit water, climbed onto land, learned to breathe oxygen, and grew into forests and whales. These microbes stayed where life may have begun. They kept the old ways, they kept the old chemistry. It is a beautiful idea, and it fits some of the evidence well, but it is not the only reading of the tree. Other researchers point out that the tree of life is hard to draw with confidence. Microbes swap genes with one another. They borrow tools from neighbors. A gene that looks ancient in one species may have been picked up much later from somewhere else. The branches blur. The root wobbles. Some studies put the hot vent microbes near the base. Other studies, using different methods, place cooler microbes there instead. So the question of whether the heat lovers are truly the oldest cousins remains open. They may be living echoes of the first cells, or they may be specialists who learned to handle heat much later, after life had already begun somewhere cooler. The genes themselves cannot quite tell us yet. What is certain is the sheer toughness of these creatures. Some archaea can survive being frozen solid for thousands of years and wake up when the ice melts. Some can repair their own broken genes after doses of radiation that would shatter a human cell. Some live in the hot rocks beneath the sea floor, at depths where no sunlight has reached for billions of years. The deepest microbes ever found were pulled from cores drilled nearly 3 miles into the crust beneath the Pacific. They were alive. They were eating. They were dividing, though so slowly that a single generation might take 1,000 years. That slowness is its own kind of record. A microbe that divides once a millennium is barely living by our standards. It is more like a small chemical machine ticking over in the dark, sipping hydrogen, releasing methane, waiting. Some of the cells now alive in the deep crust may be older than the pyramids. A few may be older than written language. We do not really know how to measure their age, because they blur the line between living and merely persisting. When you stand back and look at all of this, the deep vents start to seem less like a strange corner of biology, and more like a window into a deep past. The microbes there do not need the sun. They do not need oxygen. They do not need the surface world at all. They live as the earliest cells may have lived, in warm, dark water flavored with metals and gas. Whether they are our cousins, our memories, or simply our neighbors, remains a question for another night. Step closer in your mind and let the scale of the question shrink for a while. Forget the towering chimneys and the wide black plain of the seafloor. Picture something much smaller. Picture the tip of a needle, and then something smaller still. Picture the thinnest layer of mineral, only a few atoms thick, sitting at the edge of a tiny pore inside a vent. This is where the puzzle of life's beginning truly lives, not in grand storms or great oceans, but in the quiet meeting of a few molecules, somewhere in the dark. The question sounds simple at first. How did chemistry turn into biology? How did atoms that did not care about anything become cells that wanted to keep living? The honest answer is that no one knows. Many smart people have spent their whole working lives on this question, and the question is still open. What they have found are clues, little patterns, hints in the rock, hints in the chemistry, hints in the way modern cells still seem to remember something very old. One of the smallest, most beautiful clues hides in the membranes of living things. Every cell on Earth keeps itself separate from the world with a thin skin made of fat-like molecules. These membranes do something strange. They hold a tiny difference in charge between the inside and the outside. The inside is a little more negative. The outside is a little more positive. Cells use this difference to make energy. It is, in a sense, a tiny battery. And here is the quiet detail that some researchers find lovely. The walls of alkaline vents at places like the Lost City hold a similar kind of difference all on their own. The fluid inside the pores is less acidic than the seawater outside. Across that thin mineral wall, a gentle gradient forms, with no life needed to make it. Some scientists wonder if early life simply borrowed this gradient. They imagine the first protocells nesting inside these vent pores, using the natural difference in chemistry as a free source of energy. They did not have to invent the battery. The rock had already built one. Other researchers are less sure. They point out that real cells use very specific proteins to manage their gradients, and that bridging the gap between a raw mineral wall and a living membrane is still mostly guesswork. Both views sit on the table, side by side. There are other small details that catch the eye under a microscope. The inside of a vent chimney can look like a sponge. Tiny rooms, each no wider than a single bacterium. Some are connected by even thinner tunnels. Some are closed off. The walls are made of iron and sulfur and other minerals that, in modern cells, still sit at the heart of the proteins that handle energy. Iron-sulfur clusters, they are called. They are ancient pieces of chemistry. They show up in nearly every living thing. One idea is that these clusters were first formed on vent walls, where iron and sulfur sit ready to meet. Another idea is that they came together somewhere else entirely, and the vents are only one stage on a longer road. Then there is the matter of time. The earliest fossils of cell-like shapes are billions of years old. They are tiny. They are easy to mistake for plain mineral grains. Geologists who study them have to look very carefully, slicing rocks thinner than paper and shining light through them. Sometimes they find ghostly little circles lined up in patterns that look biological. Sometimes the same patterns can be made by chemistry alone, with no life involved. The debate over which is which can go on for decades. A rock from Western Australia, or from Greenland, or from northern Canada, can be argued over for whole careers. There is a quiet humility in all of this. The people who study the beginning of life have learned to be careful. They do not say, "This is how it happened." They say, "Here is one path the chemistry might have taken. Here is another. Here is what we can test. Here is what we cannot yet reach." The truth is that the first living thing did not leave a clear note behind. It left only the chemistry passed down to everything that came after, and the rocks it may have touched on its way. So we sit with the smallness of it, a pore in a chimney, a gradient across a thin wall, a cluster of iron and sulfur no wider than a thought. Somewhere in details like these, the answer may be waiting, or it may be hiding somewhere we have not yet looked. The question of where life began is older than the science we now use to ask it. For most of human history, the answer lived in stories and not in laboratories. Then, in a quiet century of letters and notebooks, a few thinkers began to wonder if the answer might be written into the chemistry of the earth itself. The story of how we came to suspect the deep vents begins, oddly enough, not in the ocean, but in a short private note written by a famous naturalist in the year 1871. Charles Darwin was sitting at his desk in the English countryside, writing to a friend named Joseph Hooker. In the middle of the letter, almost as a passing thought, he sketched an idea. He wondered if life might have begun in some warm little pond full of ammonia and salts, with light and heat and electricity nearby. He guessed that simple chemicals might have combined there, slowly, to form the first living things. He did not press the idea. He simply set it down and moved on. But that one sentence, written in soft ink on a sheet of paper, would shape the way scientists thought about life's beginning for the next 100 years. For a long time, Darwin's warm pond was the leading picture. It felt right. The early earth was warm. Shallow pools were easy to imagine. Lightning could provide energy. The sun could shine down and drive reactions on the surface of the water. The pond was a place a person could picture. It belonged to the world we know. In the 1920s, two researchers working far apart from each other gave the warm pond idea its scientific shape. A Russian biochemist named Alexander Oparin and a British scientist named John Haldane proposed that the early atmosphere of Earth was very different from today's. They imagined an air rich in methane and ammonia and hydrogen, with almost no free oxygen. In that strange sky, sunlight and lightning could spark chemical reactions. The products would rain down into the seas and ponds. Over long stretches of time, a kind of thin soup would form. From that soup, the first life might emerge. Then, in 1953, a young graduate student named Stanley Miller tried to test the idea. He worked in a laboratory at the University of Chicago under the guidance of his mentor, Harold Urey. Miller set up a closed system of glass flasks and tubes. He filled it with water and the gases that Oparin and Haldane had described. He passed electric sparks through the mixture to mimic lightning. He let the apparatus run for a week. When he opened it, the water inside had turned a faint brown. He tested it inside. He found amino acids, the small molecules that proteins are built from. The result was startling. In a single week, in a small glass flask, the building blocks of life had appeared on their own. For a generation, the warm pond seemed almost proven. The chemistry worked. The story made sense. But over the following decades, new questions began to gather. Geologists studied ancient rocks and decided that the early atmosphere may not have been as rich in methane and ammonia as Oparin had imagined it. May have been thinner, more neutral, less helpful to the kind of reactions Miller had run. Without that special air, the warm pond became harder to defend. Sunlight, too, came under suspicion. The young sun gave off bursts of harmful radiation that may have broken apart the very molecules a pond was trying to build. Other ideas rose up to compete. Some researchers wondered if life had begun in clay sediments, where mineral surfaces could line up small molecules and help them link together. Others looked at icy environments, where freezing could concentrate dilute chemicals into pockets of usable strength. Still others, in the late 1970s, turned their eyes downward, toward a discovery that had just changed everything. Submersibles had found black smokers on the floor of the Pacific. There was life down there in the dark, thriving without sunlight, drawing energy from minerals and heat. Some scientists began to ask whether the cradle of life had been on the surface at all. The warm pond did not vanish. It is still considered, still studied, still defended by serious researchers who believe the surface offered something the deep ocean could not. The vent hypothesis did not replace it. The two ideas now sit side by side, each with its own strengths, each with its own gaps. The question of where life began turned out to be far older than Darwin's letter, and far harder than his quiet sentence suggested. The pond and the vent are still arguing, gently, across the long silence of deep time. For most of human history, if you had asked where life began, the answer would have pointed towards sunlight, a warm pool, a shallow lagoon, a pond at the edge of a quiet sea, where the sun could pour energy into the water and stir the first stirrings of chemistry. It was a gentle picture, and it made intuitive sense. Light meant warmth, warmth meant motion, motion meant the slow mixing of molecules that might, given enough time, begin to whisper the first faint signals of life. So it surprises many people to learn that a growing number of researchers now look in the opposite direction. They look down. They look into the cold, lightless dark, miles beneath the surface, where no sunbeam has ever fallen. And they wonder if life began there instead, in the strange chemistry of the vents. This idea seems backward at first. The deep sea feels hostile to us. It is crushing. It is freezing in most places, scalding in others. It is utterly black. And yet, when researchers list the things that early life would have needed, the vents keep appearing on that list. Steady energy, steady warmth, steady minerals, steady supplies of the simple molecules that chemistry can fold into something more. The surface of the early Earth, by contrast, may have been a far harsher place than Darwin pictured. The young sun was dimmer, but the sky was wild. Meteors fell often. Ultraviolet light poured down without the protective shield of an oxygen-rich atmosphere. A warm little pond at the surface might have been bathed in radiation, strong enough to break apart the very molecules it was trying to build. Some researchers wonder whether the surface was simply too unstable, too exposed, too easily disturbed for the slow, patient work of chemistry to take hold. The deep sea offered shelter. The vents offered shelter with a furnace attached, and that combination, sheltered warmth with a constant flow of reactive chemicals, is the kind of place where a careful chemist might choose to set up an experiment that needs to run for 1,000,000 years without interruption. There is another surprise hiding in this idea. Life, at its most basic level, runs on a kind of chemistry that looks oddly familiar to the chemistry of vents. Every living cell, from a bacterium to a blue whale, generates its energy by pushing charged particles across a thin membrane. The charge difference on one side versus the other drives the machinery of life. It is a strange ancient trick, and no one is entirely sure why life chose it. But the alkaline vents at places like Lost City do something remarkably similar. The fluid inside the chimney is alkaline. The seawater outside is slightly acidic. Across the thin mineral walls, a natural charge difference forms, all by itself, with no living thing required. Some researchers find this resemblance too striking to be coincidence. They wonder if life learned the trick from the vents, copying a pattern that the rocks were already performing. Others are not so sure. The resemblance might be real but shallow, the kind of echo that nature produces by accident. The question remains open, and probably will for a long time. The vents also offer something that warm ponds struggle to provide, which is concentration. In an open pool, useful molecules tend to drift apart. They dilute, they scatter. But the porous walls of a vent chimney are riddled with tiny chambers, each no bigger than the eye of a needle, where fluids can pool and gather. Molecules can become crowded. Crowded molecules can react. Reactions can build on one another. Some researchers find this the most compelling clue of all, the suggestion that the chimneys are natural test tubes, ready-made for the slow assembly of complexity. And yet, the warm pond idea has not gone away. Other researchers point out that the chemistry of life uses certain molecules that are easier to make at the surface than at depth. They argue that wet and dry cycles of the kind a shallow pool would experience may have been needed to drive the right reactions. The vents have their puzzles too. The math of how organic molecules survive the vent's own heat is still being worked out. So the strange truth is this: the place that once seemed the least likely cradle for life has become one of the leading candidates. The dark, crushing, scalding deep is now where many researchers go looking for our beginning. Whether they are right, or whether the warm ponds will reclaim the answer, no one can yet say. The deep keeps its secret patiently, the way it keeps everything. Two simple gases sit at the heart of the deep vent story: hydrogen and carbon dioxide. They are among the most ordinary molecules on Earth, and yet they may hold the key to one of the largest questions we can ask. To understand why, it helps to follow each one from its quiet source into the strange chemistry that happens when they meet in the dark. Hydrogen comes from the rock itself. When seawater seeps down into the warm crust beneath the ocean floor, it meets a green mineral called olivine. Olivine reacts with water in a slow process called serpentinization. The rock pulls oxygen from the water and leaves hydrogen behind. The hydrogen rises through the cracks, dissolved in the warm fluid that eventually pours out at vents like Lost City. It is a gas made by the planet's own bones, given off as the crust slowly turns into softer, greener stone. Carbon dioxide arrives by another path. The deep ocean is rich in it, carried down from the surface, released by underwater volcanoes, dissolved into the cold, dark water in vast amounts. At a vent, these two gases meet. Hydrogen wants to give away electrons. Carbon dioxide is willing to receive them. In the right conditions, they can react and form simple organic molecules, small carbon chains, the first whispers of the chemistry that living cells still use today. This is the quiet symphony that fascinates so many researchers. Plate tectonics push the seafloor apart. Fresh rock rises from below. Seawater works its way into the cracks. The slow reaction with olivine makes hydrogen. Volcanism and ocean chemistry deliver carbon dioxide. Heat from the mantle drives the warm fluid upward. Mineral chimneys grow from the dissolved metals, and inside their porous walls, hydrogen and carbon dioxide come together in a way that, on the surface, almost never happens on its own. The connection reaches further still. The same reaction that makes hydrogen at the vents also changes the ocean's chemistry over long stretches of time. Serpentinization locks carbon into stone. It alters how much carbon dioxide stays dissolved in the deep. It even affects the slow balance of the climate across millions of years. The deep vents are not isolated curiosities. They are stitched into the great breathing of the planet. In modern living cells, something remarkable happens that echoes this old chemistry. Many microbes still feed by combining hydrogen and carbon dioxide. They use the energy to build the carbon-based parts of their bodies. The enzymes that carry out this reaction often contain iron and nickel and sulfur, the same metals that crystallize inside vent chimneys. Some researchers see this as a fingerprint. They wonder whether the first chemistry of life borrowed the metals it found at the vents, and whether modern cells still carry that borrowing in their oldest machinery. Others are not convinced. They point out that life is clever and may have stitched together its tools from many sources. The fact that an enzyme uses iron and sulfur today does not prove that iron and sulfur shaped the first reactions 4 billion years ago. The pattern is suggestive. It is not a closed case. Still, the symphony is hard to ignore. The sun warms the surface ocean. Wind drives current dioxide into the deep. Plates pull apart on the seafloor. Mantle heat melts rock. Water meets olivine. Hydrogen rises. Chimneys grow. And in their warm, porous walls, two simple gases find each other and react in ways that mirror the chemistry of every living thing. There is a beauty in how each part needs the others. Without plate tectonics, there would be no fresh rock for the water to react with. Without the ocean, there would be no water to seep into the crust. Without volcanism, the supply of carbon dioxide would falter. Without the heat of the deep earth, the warm fluid would never rise. The vents are the place where all of these systems converge, and they may also be the place where their convergence produced something new. What we do not know is whether this convergence was enough. The reactions that make small organic molecules from hydrogen and carbon dioxide are real and measurable. The leap from those small molecules to a living, copying, growing cell is still vast. Some researchers think the vent chemistry naturally guides matter across that leap. Others suspect the leap required something else, somewhere else, perhaps a different setting entirely. So the question rests gently on these two ordinary gases. They meet in the dark again and again, as they have for billions of years, whether they once met in a way Inside an alkaline chimney, the rock is not solid all the way through. It is full of tiny holes. Picture a sponge made of stone, with millions of small chambers nested together. Each chamber is no wider than a single cell, sometimes smaller. Seawater seeps through these pores in slow, quiet currents. This porous structure may be the most interesting thing about white smokers, at least when it comes to the question of where life began, because life, at its simplest, needs a container, something that holds molecules close together, something that keeps the inside different from the outside. A modern cell does this with a thin skin made of fats, but before fats existed, before any cell wall had been built, something else had to do the job. And one idea is that the rock itself did it. The pores in these chimneys form when warm alkaline fluid meets cold seawater. Minerals fall out of the fluid and stack into thin walls. The walls grow around bubbles and gaps. Over years and decades, the chimney grows taller and more complex, with pore inside pore inside pore. Each little chamber traps fluid. Each chamber has a slightly different mix of chemicals than the chamber next to it. That detail matters. In a flat open ocean, any molecule that forms quickly drifts away. It gets too thin, too spread out, to ever meet another molecule and react. But inside a pore, things stay close. Molecules bump into each other again and again. Concentrations can build up, and the rock walls themselves may have helped certain chemical steps along, acting like tiny workbenches where reactions happen more easily. Some researchers think this is how the first protocells took shape, not as free-floating bubbles in an open sea, but as fluid trapped inside stone. The chimney would have been the body. The chemistry of life would have unfolded inside a mineral skeleton. Only later, the idea goes, did some of these chemical systems learn to build their own walls out of fats and float away on their own. It is a beautiful picture, but it remains a hypothesis, not a fact. Other researchers point out that we have never seen this actually happen. No experiment has yet taken a porous mineral chamber and grown a true protocell inside it. We have made small steps. We have shown that certain molecules will gather inside lab-made pores. We have shown that fatty membranes can form under vent-like conditions. We have not closed the gap between interesting chemistry and something that could be called alive. The other open question is time. These chimneys do not last forever. A black smoker may stand for only decades before it collapses. White smoker towers, like those at the Lost City field, last much longer, perhaps tens of thousands of years, maybe more. But even that is short compared to the slow work of evolution. If life needed millions of years to assemble itself, a single chimney could not have held the whole story. The setting would have had to repeat itself over and over across many vents and many ages of the early ocean. So the picture changes as we think about it. Not one chimney, but a field of them. Not one moment, but a long, slow rhythm of growth, collapse and rebuild. Each new tower would have started fresh, with new pores and new fluids, perhaps carrying forward a few molecules from the wreckage of older towers nearby. Life, if it began here, may have begun many times before it finally stuck. And the Earth itself was changing while this was happening. The young ocean was hotter than today's ocean. The atmosphere held almost no oxygen. The sky may have looked orange or hazy. Volcanoes erupted often. The crust was thinner, the mantle warmer, the vents more numerous and more violent. Whatever environment cradled the first cells, it would not look like the ocean we know now. It would look stranger, dimmer, more restless. We can try to picture those ancient chimneys standing in that ancient sea. Pale towers rising through black water, warm fluid drifting up through countless tiny chambers. Inside each chamber, a slightly different mix of molecules, sitting close, reacting, settling, reacting again. Somewhere in all that slow, quiet chemistry, something may have crossed a line we still cannot define. Or it may not have happened there at all. It may have happened somewhere else, in some setting we have not yet thought of, and the vents simply hosted later life without inventing it. The pores in the rock are a wonderful clue. They are not, on their own, an answer. The question keeps its patience and waits. In the world above the waves, light shapes almost everything. Plants drink it, eyes catch it. Even the colors of stones and skies are stories told by light. But far below, where the vents rise from the sea floor, there is no light at all. The water is black as ink, and the only glow comes from the faint shimmer of hot fluid mixing with coal. And yet, somewhere in that perfect darkness, the question of how life learned to write itself may have first been answered. Life uses a code. Inside every living cell, there are long molecules that carry instructions like tiny ribbons of memory. We call them nucleic acids. The most famous is DNA, the double helix that holds the recipe for a body. But there is an older, simpler cousin called RNA. It is a single strand, more fragile, more flexible, and many researchers believe that RNA, not DNA, was the first code of life. The idea is called the RNA world. In this picture, the earliest living things were not cells with elaborate machinery. They were small loops and strands of RNA, drifting in some quiet pocket of early Earth, copying themselves and slowly getting better at it. RNA is special because it can do two jobs at once. It can store information like a written page, and it can fold into shapes that act like little tools, speeding up chemical reactions. A molecule that is both message and worker is a very good candidate for the start of life. But the RNA world has a problem, and the problem is the vents. To build a strand of RNA, you need certain building blocks. You need sugars, you need bases, you need phosphates. You need them clean, and you need them concentrated in a warm little pond at the surface, drying and refilling with each rain. Those ingredients might gather and stick. The sun could drive reactions. The shore could leave salty crusts behind. Some chemists argue this is exactly the kind of place RNA could first appear. The vents, by contrast, are wet all the time. They are dark, they are hot in places, and they are flushed by endless currents of seawater. Critics of the vent hypothesis ask a sharp question: how could fragile RNA strands ever form in such a place, when water itself tends to pull them apart? It is a fair worry. RNA, in open seawater, does not last long. The bonds that hold its letters together loosen and break in warm, wet conditions. Supporters of the vent idea answer with the chimneys themselves. They point to the tiny pores in the mineral walls, the soft honeycomb of alkaline vents like lost city inside those pores. The chemistry is different. Hydrogen flows in from below, carbon dioxide drifts in from the sea. The walls themselves carry electrical gradients, faint currents born from the meeting of two waters. In those small dark chambers, some researchers wonder, the building blocks of RNA could have been trapped, concentrated, and protected from the open ocean. There is even a quiet possibility that minerals played the role of light. On the surface, some light gives energy to drive reactions forward. At the vents, the energy comes instead from chemistry. Iron and sulfur compounds in the chimney walls can pass electrons back and forth, almost like the green machinery inside a leaf. Some scientists think these mineral surfaces could have acted as the first catalysts, helping simple molecules link into longer ones. The light of the sun and the slow glow of mineral chemistry would, in this view, be two different paths to the same beginning, yet nothing is settled. Laboratories on the surface can now make short strands of RNA in conditions that mimic warm ponds. Other laboratories can make interesting molecules in conditions that mimic vents. Both sides have evidence. Neither side has the whole story. We do not know which environment, if either, truly hosted the first faint copy of a self-replicating lipid. It is strange to imagine that the code which now writes redwoods and whales and human dreams may have first been written in absolute darkness. No sun touched it, no shadow fell across it. The only light, if you can call it that, was the slow shine of chemistry doing its patient work in stone. Or perhaps the first code was written under a pale early sun in a shallow pool that has long since dried away. We do not know which picture is right. We may never know. The light that would tell us is a light from 4 billion years ago, and it has long since faded. What remains is the question, drifting quietly in the dark water, waiting for someone to listen a little closer. If you could lower a microphone deep into the ocean, down past the sunlit waters, and into the cold dark where the vents stand, you would not hear silence. The deep sea hums, water moves in slow currents around the chimneys. Hot fluid hisses as it meets the cold. Minerals settle and shift, and now and then the seafloor itself groans as plates grind below. The sound of a vent field is a low, patient breath, steady and slow, the kind of sound that feels older than memory. That breath may not belong to Earth alone. Some of the most interesting moons in our own neighborhood appear to hide oceans beneath their icy shells. Saturn's moon Enceladus shoots tall plumes of water vapor from cracks near its south pole. Spacecraft have flown through those plumes and tasted them, and what they found was striking. There was water, there was salt, there were simple carbon molecules, and there were hints of hydrogen, the same hydrogen that pours out of alkaline vents on our own seafloor. Jupiter's moon Europa tells a similar story. Its surface is a smooth shell of ice, cracked and refrozen many times. Beneath that shell, most researchers believe, sits a salty ocean perhaps twice the volume of all the oceans on Earth. The rocky floor of that ocean may press against warm interior rock. If it does, there could be vents there too, slow chimneys building themselves in the dark of a world far from the sun. This is where the question of vents and the question of life begin to widen. If life on Earth started in hydrothermal systems, then any world with similar systems might hold the same possibility. The chemistry needed is not exotic. Water, rock heat, and a steady flow of simple molecules. These ingredients seem to exist in more than one place in our solar system. Some researchers find this thrilling. Others remind us that possibility is not proof. A kitchen full of ingredients is not the same as a cake. The sounds these distant vents might make are, for now, only imagined. No microphone has yet listened to the seafloor of Europa or Enceladus. Future missions may carry instruments that can pick up the faint vibrations of cracking ice or shifting water. Scientists have already turned data from spacecraft into audio, translating magnetic fluctuations and plasma waves into eerie tones that drift and shimmer. These are not true sounds of those worlds, only mathematical sketches of them. Still, they invite the ear to wonder what a hidden ocean might whisper if we could only listen. There is a competing view worth holding. Some researchers argue that even if vents exist on other moons, the chemistry there may differ from Earth's in ways that matter. The rocks may be different, the pressure may be too great, or the chemistry too slow. Just because vents are present does not mean life will follow. Earth had 4 billion years, an entire planet of varied environments, and we still cannot say for certain where or how life began here. To expect a clear answer from a moon we have barely visited may be asking too much, too soon. And yet the question pulls at us. If life began at vents on Earth, and vents exist elsewhere, then life may not be a single accident on a single world. It may be a recurring pattern, a chemistry that finds its way wherever the right conditions meet. If instead life began somewhere else on Earth, in a warm pool, on a tidal flat, in a sheet of clay, then vents may be only one of many possible cradles, and the moons of the outer planets may still be silent. The instruments that might one day tell us are slowly being built. A future spacecraft may drill through the ice of Europa. A small craft may fly again through the plumes of Enceladus and sample them with finer tools. Each piece of data will be turned into numbers, and some of those numbers may be turned into sound, so that we can hear in our own translation what those hidden oceans are doing. For tonight, the question rests where it has rested for some time. The vents of Earth breathe steadily in the dark. The moons turn in their slow orbits, their inner oceans moving in ways we can only guess at. Somewhere on the sea floor of a distant world, a chimney may be growing, mineral by mineral, just as the chimneys here grow. Or there may be nothing at all, only cold rock and quiet water. We do not know. We may not know for a long time. The listening has only just begun, and the sound that returns will be patient and faint and worth waiting for. Deep inside ancient rocks, in places where the crust has not been disturbed for billions of years, geologists look for something very small. They look for shapes inside stone, tiny tubes, faint threads, little dots, arranged in patterns that hint at something that was once alive. These are the candidates for the oldest fossils on Earth, and the numbers attached to them are almost too large to feel. The Earth itself is about 4.5 billion years old. The oldest rocks we can still find on the surface are roughly 4 billion years old. That gives life only a narrow window of time to appear, take hold, and leave a trace we can still read. Some scientists believe that window may have been even shorter than we once thought. The math is gentle, but it presses on us. Life seems to have started very soon, after the planet cooled enough to hold liquid water. In northern Quebec, a band of dark rock called the Nouveau-Guituk Belt holds some of the oldest stones we have ever touched. Within those stones, researchers have found tiny tubes and filaments made of iron-rich minerals. They look strikingly like the structures that modern bacteria build around hot vents. If those shapes really are fossils, they would push life back to somewhere between 3.7 and 4.3 billion years ago. That older figure would mean life appeared almost as soon as oceans existed. Not everyone agrees. Some geologists argue the tubes formed through ordinary chemistry, with no living thing involved. Minerals can grow in tube-like shapes when hot fluids mix with cold seawater. The patterns are suggestive, but suggestion is not proof. The debate runs quietly through journals and conferences, and the rocks themselves keep their secrets. Other ancient candidates sit in the cherts of Western Australia, in formations called the Apex Chert and the Strelly Pool. There, scientists have found dark threads in stone that may be the remains of microbial mats. Some are dated to around 3.5 billion years ago. The numbers are slightly younger than the Quebec tubes, but the evidence is in some ways more accepted. Even so, doubts remain. Each candidate fossil is studied, questioned, and studied again. The beauty of the math is in the ratios. Carbon comes in two stable forms, carbon-12 and carbon-13. Living things slightly prefer the lighter one. When organisms build their bodies, they pull in a little more carbon-12 than the surrounding rock contains. This leaves a faint signature, a small imbalance, that geologists can measure billions of years later. In some of the oldest rocks, that signature is there. Carbon trapped inside ancient stone leans toward the lighter form, just as it would if life had once handled it. The signal is small. The difference is only a few parts per thousand, yet the same imbalance appears in living things today, in the leaves of trees and the shells of plankton, and the cells of vent microbes. A ratio measured today in a fresh sample matches a ratio measured in a rock nearly 4 billion years old. That quiet agreement is one of the most haunting pieces of evidence we have. Still, ratios alone cannot prove that life existed. Some chemical processes without life can shift carbon in similar ways. The numbers point gently in a direction, but they do not close the case. Researchers must combine the carbon evidence with the shapes in the stone, the chemistry of the surrounding minerals, and the geological setting of the rocks. Each layer of evidence is a small probability. Together, they build a picture that is suggestive, but never quite certain. If life did begin at hydrothermal vents, then the oldest fossils should sit in rocks that once formed near such vents. Several of the candidate sites do exactly that. The Nouveau-Argituc tubes lie in stones that may have been part of an ancient seafloor with hot springs. The Australian cherts include layers that could have formed near warm, mineral-rich waters. The geography of the evidence quietly favors the vent hypothesis, though it does not seal it. The mathematics of deep time is patient. A few 100 million years here, a few 100 million there, and yet each rock holds a moment. A single, thin section under a microscope can show a pattern that took only days to form and then waited 4 billion years to be seen. The window of life's beginning in the long arithmetic of the planet is narrow and bright and still mostly dark to us. The numbers point, the shapes whisper, the rocks remember more than they tell, and we keep listening, slowly, with quiet wonder. Think, for a moment, about how little of the deep ocean floor we have actually seen with our own instruments. The seabed covers roughly 70% of our planet's surface, and yet only a small fraction of it has been mapped in fine detail. Most of what we have charted comes from satellites that read the shape of the sea surface above, which gives us a blurry sense of the mountains and trenches below. The sharper maps, the ones that show individual chimneys and small ridges, cover only narrow strips where ships have passed with sonar. The rest is still, in a real sense, unknown country. This matters for the mystery we have been sitting with. If life began at hydrothermal vents, we would want to know how many vent fields exist, where they cluster, and how their chemistry varies from place to place. We have found something like 700 active vent fields so far. Researchers suspect there may be many more, perhaps 1,000 or 2,000, hidden along ridges and back arc basins we have not yet visited. Each one is its own small experiment in chemistry. Each one could hold clues we have not gathered. The conditions that make these vents possible are themselves a fragile balance. Earth sits at a distance from the sun, where water can stay liquid across most of the surface, neither boiling away nor freezing solid. The planet still has enough internal heat left over from its formation and from the slow decay of radioactive elements deep inside, to drive plate tectonics. Without that heat, the seafloor would not spread, ridges would not form, and seawater would not circulate through hot rock. The vents would simply go quiet. The atmosphere plays its own role in this balance. It holds in just enough warmth to keep the oceans from freezing to the bottom, and it shields the surface from the harshest radiation. The chemistry of the air and the chemistry of the sea are linked in slow loops that have run for billions of years. Carbon moves from volcanoes into the air, into rain, into the sea, into shells and sediments, and eventually back down into the mantle through subduction zones. If any link in that loop broke for long enough, the surface conditions would drift. It is worth pausing on how unlikely all of this seems, taken together. A rocky planet of the right size, holding onto an atmosphere of the right thickness, orbiting at the right distance, with a molten interior that has not yet cooled, with oceans that have neither boiled nor frozen, with continents that drift and recycle. Change any one of these things too far, and the chimneys at the bottom of the sea would never have formed. Change a few of them, and life, if it began at the vents, would have had no cradle at all. And yet we still do not know how narrow the window really is. Some researchers argue that life is robust, that it would find a way under a wide range of conditions. They point to microbes living in boiling acid, in deep ice, in rocks kilometers below the surface. Others argue that the chemistry of beginning is far more delicate than the chemistry of surviving. Starting from nothing, they suggest, may require a very specific kind of place. The vents fit that description for some. For others, the warm, shallow pools fit it better. The disagreement is honest, and it is not close to settled. What we lack in part are the maps. We have not drawn a complete picture of where alkaline vents like the Lost City form, how long they last, or how common they were in the early Earth's oceans. The young planet had a different crust, a different ocean chemistry, a different atmosphere. The vents of 4 billion years ago may have looked nothing like the vents we visit now. Some scientists wonder whether the Lost City field, with its tall, pale towers and its quiet alkaline fluids, is a faint echo of a much more common kind of place long ago. Others suspect it is unusual now, and was unusual then. Until we have better maps both of the modern sea floor and of the ancient one preserved in old rocks on land, the question stays open. The fragile balance that allows vents to exist at all is part of what makes the mystery so striking. A planet had to be steady enough to hold its oceans for billions of years, and restless enough to keep its chimneys burning. Earth somehow has been both. Whether that combination is the recipe for life, or only the stage on which life happened to appear, is something we still cannot say. To reach the vents, you must first descend, and descending in the deep ocean is harder than almost anything else humans try to do. The water above presses down with a weight that would crush an ordinary submarine like a soda can in a closed fist. So the small craft built to visit hydrothermal fields are not really submarines in the usual sense. They are tiny spheres of thick metal, just large enough for 2 or 3 people to fold themselves inside, sealed against a darkness that does not forgive mistakes. The most famous of these little spheres is the one that first carried scientists to the black smokers in the late 1970s. It moved slowly, sipping power lit only by small lamps that pushed back a few meters of water at a time. Beyond that ring of light, the ocean was perfectly black. Inside, the air was cold and the metal walls sweated. The people inside wore wool hats and tried not to think too hard about the pressure pressing in from every side. Many of the questions we have been wondering about together can only be answered by going down there. You cannot study a vent from the surface. You cannot lower a bucket and bring up a chimney. You have to send something. A person, a robot, a clever little arm, straight into the dark and back again. That is harder than it sounds. The deep ocean swallows things. Cables snap, lights fail, currents move in slow rivers no one can see. Over the decades, several deep diving craft have been lost to the sea, sometimes with people inside, sometimes empty. The losses are quiet, almost private. The ocean closes over them and goes on as before. Because of that risk, most of our maps of the deep are still mostly blank. We have studied only a small fraction of the global vent system. Most of the chimneys that exist along the long mid-ocean ridges have never been seen by any eye, human or mechanical. There are likely entire vent fields out there that no one has named, no one has sampled, no one has even noticed from the surface. That gap matters for the central question of this episode. If life began at a hydrothermal vent, then somewhere on the modern seafloor there may be a kind of vent that most closely resembles the cradle. The exact chemistry, the exact mineral mix, the exact temperature gradient. We may have already found it at Lost City. We may not have found it at all. The right vent might be sitting in the dark right now, in a part of the ocean no submersible has ever visited. There are other unsolved pieces too. We still do not know how long an individual chimney can keep going. Some seem to fade in decades. Others, like the towers at Lost City, may have stood for tens of thousands of years. We do not know how many vents are quietly hosting microbes that use chemistries we have never described. Every time a new field is explored, new microbes turn up, and some of them sit on branches of the tree of life that nobody expected. We also do not know how often vent ecosystems are wiped out and reborn. Underwater eruptions can bury a whole field in fresh lava. Within a year or two, the tube worms and crabs return, somehow, from somewhere. How they find a new vent across so much empty water is a puzzle that researchers are still working through. One idea is that larvae drift on slow, deep currents and get lucky. Another is that there are stepping stone vents we have not yet mapped, smaller and quieter, that keep the network linked. Each of these gaps is, in its own way, an invitation. The ocean has not handed us a finished story. It has handed us a few pages, water-stained and out of order, and asked us to guess at the rest. The submersibles that have been lost to the deep are part of the cost of trying. The submersibles that come back, with their small samples and their cold metal arms, carry pieces of a picture that is still being assembled. It is comforting, in a way, to know how much remains unknown. We tend to imagine that the great age of discovery is behind us, that the maps are finished and the frontiers all closed. The deep sea quietly disagrees. Most of it has never been seen. Most of its chimneys have never been counted. Most of its creatures have not been named. Somewhere down there, in a place no light has ever reached, a slow tower of mineral is building itself, one crystal at a time, and no one yet knows it is there. The vents we have been wondering about are not still and unchanging. They live in their own slow way. They are born, they grow, they fall silent. A black smoker may stand and steam for decades, then go cold when the cracks below it shift and the hot water finds a new path through the rock. The chimney that fed a forest of tube worms becomes a quiet ruin, its minerals slowly dissolving back into the sea. So when we ask what will happen to the deep vents in the far future, we're really asking about something that has always been changing. The vents are not a place, they are a process. As long as there is water above hot rock, somewhere on this planet, there will be vents of some kind, and the rock beneath the ocean is restless on a scale that humbles every clock we own. In a million years, the vent fields we have mapped today will almost certainly be gone. New ones will have opened where the seafloor has cracked fresh seams. The lost city field, with its pale towers of carbonate, may still be standing, since alkaline vents like it can last for tens of thousands of years, perhaps longer. Some researchers wonder if a few of its spires might persist for 100,000 years or more. Even so, on the longer scale, even lost city will fade. Other fields, unknown to us now, will be rising in the dark. In 100 million years, the very shape of the ocean floor will look different. The mid-ocean ridges, where most vents form, are slowly rearranging themselves. The Atlantic will be wider, the Pacific will be smaller. New ridges will tear open, where today there is only quiet abyss. Whole vent ecosystems will have come and gone many times over. The tube worms, the pale crabs, the strange microbes, their descendants, if any survive, may look quite different, or they may be replaced by something we cannot yet picture. In a billion years, the question grows harder. The sun is slowly brightening. In about a billion years from now, some climate models suggest the oceans may begin to evaporate as the planet heats. If that happens, the vents would lose the very thing they need, the cold, heavy sea pressing down on hot rock. Without the ocean, there are no black smokers, no white smokers, no lost city. The chimneys would stand exposed and dry, slowly crumbling into dust. This is one possibility. Others wonder whether some pockets of water might linger far longer, in deep basins or beneath an icy crust if the planet cools again in some unexpected way. The future of Earth's water is itself an open question. There is something gentle in this thought. If life truly began at vents, then the same kind of place that cradled the first cells may also be among the last places where simple life endures. Some researchers have wondered whether deep, hot, mineral-rich waters far beneath the seafloor might shelter microbes long after the surface has grown harsh. The first cradle and the final refuge could be the same kind of darkness. We do not know if that picture is right. It is only one of many ideas about how life might fade or hide when the planet changes. There is also the question of what we do in the much nearer future. The deep ocean floor holds metals that humans want: copper, zinc, gold, rare elements bound up in the very chimneys we are still trying to understand. Some companies and nations have begun looking at deep-sea mining. Researchers worry that if we break apart these structures before we learn what they hold, we may lose answers we did not know to ask. The vents have stood quietly for as long as Earth has had oceans. They are fragile in a way that is hard to measure, because we still do not know what they contain. For tonight, none of this needs to be solved. The vents are still there, in the dark, doing what they have always done. Hot water rises, minerals settle, strange creatures cling to the warmth. Somewhere, a new chimney is beginning to grow, only a few centimeters tall, with a long life of slow building ahead of it. Somewhere else, an old one leans and finally falls, its work done. A million years from now, the map will be different. A billion years from now, the map may not exist at all, but the slow chemistry of water and rock and heat, the chemistry that may have started everything, will go on for as long as this planet can hold it. And in some quiet pocket of the deep, that chemistry is still writing the same patient story it has always told. Let us step back now, as far back as it is possible to step, Let the chimneys of the deep ocean grow small in your mind. Let the ocean itself grow small. Let the earth become a single pale stone, turning slowly in the dark. From this distance, the question we have been holding feels both smaller and larger than before. Smaller, because our whole planet is only one small stone among countless others. Larger, because if life began here, in the warm chemistry of a vent on the ocean floor, then something extraordinary happened on this one small stone. Something that may or may not have happened anywhere else. The atoms that built the first cell did not come from nowhere. The hydrogen in the seeping vent fluid is older than the Earth itself. It formed in the first minutes after the universe began, when the cosmos was still hot and bright and very young. That hydrogen has been drifting through space for billions of years. Some of it ended up in the cloud of gas that became our sun and our planet and our ocean. Some of it ended up seeping through the cracks of the seafloor, mixing with seawater, building the slow chemistry that may have led to us. The heavier atoms have a different story. The carbon in your blood, the oxygen in your breath, the iron in the rock of the chimneys, the calcium in your bones. All of these were forged inside ancient stars. Stars live for millions or billions of years, fusing light elements into heavier ones in their hot cores. When the largest of them die, they scatter those elements outward in great glowing clouds. Those clouds drift, they cool, they gather again into new stars and new planets. Our planet is made of that scattered material. The chimneys are made of it. The tube worms swaying in the dark are made of it. You are made of it. The same atoms that once burned inside a dying star are now arranged, for a little while, into a person lying quietly in bed, listening to a voice describe the bottom of the sea. This is not poetry. This is chemistry. The iron in the black smoker and the iron in your blood share a history that goes back to the same kind of stellar furnace. The carbon dioxide that seeps from a vent and the carbon dioxide you breathe out tonight are made of the same element, shaped by the same ancient processes. The line between a chimney and a body is thinner than it seems. Maybe that is what makes the question of life's beginning feel so close to home. We are asking how the chemistry of a young planet learned to fold itself into something that could ask questions. We are asking how a slow stirring of minerals and water and gas became a thing that wonders. And we are asking it from inside the very system we are trying to understand. The chemistry is asking about itself. The vents may hold the answer. They may not. The answer may lie in a warm pool on an ancient shore, or in a mineral pore deep in the crust, or somewhere none of us have thought to look. The honest position, after all these centuries of careful work, is that we do not know. We have ideas, we have evidence, we have rival theories that each capture some piece of what must have happened. We do not yet have the whole picture. That uncertainty is not a failure. It is a kind of inheritance. Every generation of curious people has stood at the edge of what is known and looked out into the dark. Some of those people once thought the earth was the center of everything. Some thought life could appear from nothing in a jar of broth. Some thought the deep sea was a desert. Each of those ideas softened as new evidence arrived. Each was replaced by something closer to true, though never the whole truth. Tonight, you are part of that long line. You are a creature made of star matter, lying on a planet made of star matter, wondering about a vent on the ocean floor, where star matter may have first learned to copy itself. The wondering is the inheritance. The wondering is what we have always done. The chimneys are still there. They are venting their warm chemistry into the cold water, exactly as they did before anyone knew they existed, exactly as they will continue to do long after this night has passed. Somewhere among them, perhaps, is the answer to where we came from. Somewhere among them, perhaps, is only more mystery. Either way, the ocean keeps its quiet, and the stone keeps turning, and the question gently remains open. And so we come to the end of our slow walk along the ocean floor. We have stood beside black smokers, throwing their dark plumes into the cold water above. We have rested at the pale spires of the lost city, where the chemistry is gentler and the towers grow slowly over many thousands of years. We have watched tube worms sway in warm currents, fed by tiny partners they carry inside their bodies. We have wondered, together, whether life itself once began in places like these. The question is still open. It may stay open for a long time. Some researchers feel that warm, shallow pools lit by the early sun are the more likely cradle. Others look to the dark vents, where hydrogen and carbon dioxide meet across thin mineral walls, and feel that something deep and ancient is whispering there. Both groups are careful. Both groups are honest about what they do not know, and the truth, when it finally settles, may be stranger than either picture. It may borrow from both. It may borrow from neither. For now, picture the planet as it really is tonight, a soft blue sphere turning slowly in the dark, most of its surface covered in water, most of that water deep and cold and quiet. Down at the bottom, far below the reach of any light, the vents are still working. They have been working for billions of years. They will keep working long after this night has passed. Mineral towers are still rising, one slow crystal at a time. Warm fluids are still rising through the rock. Tiny living things are still feeding on chemistry alone, with no sun to thank, no moon to notice them. Above them, the ocean rests. Currents move in great slow rivers around the globe, carrying heat from one shore to another. Whales sing in the middle layers, calling to one another across distances we can barely measure. Schools of small silver fish drift in the upper waters, turning together like a single soft mind. Near the surface, moonlight lays a thin path across the waves. The path moves as the water moves. It will be there tomorrow night and the night after, in some form or other, on some quiet sea. The land is resting too. Mountains stand under starlight. Forests breathe slowly in and out. Rivers run toward the sea, the way they always have. Deserts cool under a dome of stars. Somewhere a soft rain is falling on a roof. Somewhere snow is settling on a high ridge, with no one to watch it. The planet does not need us to be awake. It does its quiet work without asking anything of us. And you are part of it. The same water that pours from the vents is, in some small share, the water inside you. The same minerals that build those tall chimneys are, in some small share, the minerals in your bones. The same long story of life, whatever its first chapter turns out to be, runs through every cell that is keeping you warm under your blanket tonight. You are not separate from this mystery. You are one of its newest sentences. It is a kind thought to fall asleep with, that the question of where life began is still being asked by minds like yours, on a planet that still holds its oldest secrets gently in the dark. That somewhere right now, a small submarine is drifting near a vent, its lights catching the slow drift of mineral snow. That somewhere a scientist is looking at an ancient rock and wondering if the tiny shape inside it is a fossil, or only a trick of stone. That the answers, if they come, will come slowly, the way most true things do. You do not need to solve any of it tonight. The vents will keep their counsel. The lost city will keep growing its pale towers. The ocean will keep its long, patient rhythm. Your only task right now is to rest, to let your breathing slow, to let the warmth of the blanket settle around you, to let the soft picture of a quiet planet turning gently in the dark carry you the rest of the way. Thank you for spending this night with us. Thank you for letting your imagination wander down into the deep, where the water is black and the chimneys glow faintly, and the oldest questions are still waiting to be answered. Sleep now. The ocean is still there. The mystery is still there. And they will both be here when you wake. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.